here's the example I wanted to work through with you. It says, prove that A intersect B union C is equal to A intersect B union A intersect C. You should recognize this as one of the distributive properties because we have a mixture of intersection and union. Mixture of union and intersection. That's how you recognize that distributive property is being used. Okay, if we write what A intersect B union C means, then we can prove this statement. A intersect a set means the set of X in our universal set such that X is in A and, that's the logical and X is in B union C. Now we have the B union C that we want to write its definition. So what does it mean for X to be in B union C? That's the same as saying, after I copy all the rest, that's not changing, that's the same as saying X is in B or X is in C. So now what we're doing is using chapter 2 logical equivalences to show that this set is actually equal to the set of X in the universal set such that X is in A and X is in B. Oops. Or X is in A and X is in C. Now, if you look at the other proofs of a similar fact, you're going to have that these logical equivalences that were used get specified. So make sure you're watching for that specificity when you're working on reading these examples that are already done in the textbook. Let's keep going with definitions here. X is in A and X is in B means the same thing as X is in A intersect B. And similarly, X is in A and X is in C means the same thing as X is in A intersect C. And these two statements are joined with a logical OR. Now, remember that when I have the set of X in the universal set such that X is in one set or X is in the other, that's the definition of union. So I could write this as the set of X in U such that X is in A intersect B, union the set of X in the universal set such that X is in A intersect B. But this here is another way of just writing the set A intersect B. Oh, I just realized I made a mistake. Let me fix it. This should be a C over here. Okay, so what we have, just to review before we move to the next step, we have that A intersect B union C is equal to the set of X in U such that X is in A intersect B, union the set of X in U such that X is in A intersect C. As I was starting to say, the first set here is actually exactly what A intersect B means. So that means I'll just write A intersect B for that. And then union, similar observation for this second set. This second set is actually just A intersect C. Okay. When I do a proof like this properly, I need to make sure that I include all the reasons. Okay, so let's add those in here. First step, how do we go from the left side to this first step? Well, this is the definition of intersection. I'm going to abbreviate the word definition DEF apostrophe N. What about from this line to the next line? Notice we changed the union symbol into a logical statement involving or. So that's the definition of union that we used. Next, from here to here, we used chapter 2 logical equivalences. So specifically which one? We used the distributive property or the distributive law for logical equivalences. That's a law that we already established in chapter 2, so we can use it here if we want. All right, from this step to this step, notice we turned an AND statement into a statement involving an intersection of two sets. That's using the definition of intersection, but in the other direction. And that's totally allowed. So here we use the definition of intersection, and we actually used it twice. We used it here, and we used it here. From the current step to the next step, you'll notice we took an OR statement and turned it into a statement about a union of two sets. This is, again, the definition of union, just in the other direction. And finally, what we can say about the last step is that it's this here, the second to last step, is a way of expressing the set A intersect B. So how would we write that? What reason would we put? We can say definition of A intersect B specifically and A intersect C specifically. Because we already have that union symbol we need, we just need to rewrite each of these sets in the second to last step as something that makes more sense or just uses a different notation. Okay? All right. So now it's going to be your turn. You're going to do hands-on exercise 4.3.6. You're going to prove that if A is a subset of B and B is a subset of C, then A is a subset of B intersect C. They help you come up with some of the ideas that you're going to need to create the proof. One important thing to review is the definition of subset. So I'm going to use X and Y as my sets just so that we don't confuse it with the A and the B and the C in this exercise. So recall the definition of subset. So X is a subset of Y if and only if, for all X, if X is in X, then X is in Y. And what you recall is that proving a statement like this involves choosing an arbitrary element of the subset, or the candidate for a subset. Choose an arbitrary element. It has no special property other than the fact that you're saying it belongs to the subset, or the subset candidate. And then you do some kind of argument to show that it must also belong to the superset, the Y in this case. Special things happen when you do this kind of argument for the empty set, but what I'm describing right now is kind of the general strategy for showing that one set is a subset of another. Okay? With that piece of advice in mind, go ahead, read this discussion, do these steps where they're asking you, what are you needing to assume? What is it that you want to prove? This definition up here should help you answer that. And then there's some more discussion that continues. And this guided hands-on exercise is going to ask you to provide a final proof at the end. You can kind of do an outline that kind of summarizes and collects together everything you're going to do. Remember, you're always practicing giving a reason for each step, and then there's usually an introductory sentence and a concluding sentence, and we've seen several examples where you're doing that kind of thing.